Okay, so let's continue where we left off. So let's do some example problems. Now we have a dental hygienist. They use x-rays, 1 angstrom for the length, to take a series of dental radiographs. What's the frequency in 1/2 of the x-rays? So here we're going to have C equals R lambda times frequency. So that's the only formula we know so far. Now what do we want to solve for? We want to find the frequency. So we're going to find our nu, and what we're given is we are given our wavelength, which is in angstroms. So we're given the wavelength. How do we know it's wavelength? Well, angstroms is one of the units for wavelength. And then we know that the speed of light is 3 times 10 to the 8 meters per second. Now, if we're going to use this formula, we want to find nu. So let me solve for nu. So nu equals RC over lambda. And again, it makes sense because they're inversely proportional. So here, notice that our speed of light has the unit meter, but we have angstroms for our wavelength. So we're going to have to convert that so that way we can solve our problem. So for our lambda, if we take our 1 angstrom, we know that an angstrom, and that's going to equal 10 to the negative 10 meters. And so we get 1 times 10 to the negative 10 meters. Okay, so now we have our units that are matching, both meters, and we want to find our frequency, which is going to be 1/seconds. Okay, so let's go ahead and plug it in now. So this is just a plug and chug kind of problem. So then we've got 3 times 10 to the 8 meters per second. We're going to divide that by 1 times 10 to the negative 10 meters. Our meters will cancel, and now we're going to be left with 3 times 10 to the 18 1/seconds, or second to the minus 1. So that is our final answer for our frequency. Okay, well, I hope that makes sense. All right, now another example. Like I was explaining before, it's important to understand the spectrum for the radiation. So here we have which type of light, UV or red light, has the highest energy, longest wavelength, and highest frequency. So this will be our UV versus red light. So let's go ahead and, based on the spectrum, we know that, I'm going to go ahead and scroll back to our spectrum. We know that we have UV light here. And then in the visible part, we have our red light. We have our red light over here. So which one will have a higher energy? Well, UV light is to the left of visible, and energy increases as we go to the left towards gamma rays. So we know the highest energy then has to be our UV. So it has the highest energy, UV. And then we also know that the relationship between, for our spectrum, is that frequency goes in the same direction as energy. So what has to have the highest frequency? Well, it has to still be UV. And then we know that frequency and wavelength are inversely proportional. So we know that the longest wavelength has to be red light. So you'll see problems like these similar on your quizzes and on your homework and on an exam. So you have to be able to look at the look at the problem and understand that relationship and be able to identify what has the highest energy, lowest energy, highest frequency, lowest frequency, longest wavelength, shortest wavelength. Okay, now let's go back to light. So we said light can have wave-like behavior or particle-like behavior. Before we get into the particle-like behavior, I want to go over some differences in the behaviors of waves and particles just in general. So over here on the left side, we have waves. So boxes A and C belong to wave-like behavior. And on the right, notice it's orange on the left-hand side. Particles, it's yellow. This is going to be for particle-like behavior on the right-hand side. So let's talk about how light travels. Now, if it's wave-like, we know that, we see that when we were going to a lake or a swimming pool, we notice that light will bend. So when we go ahead and look at the light when we're out, we know that the direction of the wave, it will start to change, and it will start to what's called refract. So what's happening is that your speed of your light here changes quickly or immediately. So we get refraction. Okay, so as light hits the water, we will get refraction. So as light travels at different speeds through different type of media, this is an example of water, you get an immediate change. Now in physics, they make you determine what angle this is for your angle of diffraction, but we don't do that. I just want you to know the conceptual part of it. And then over here, what happens if you have an opening? So this is supposed to be a little opening right here. And what happens as your wave strikes an edge of an object? Well, what happens is that if it's wave-like, we know that it bends around it. And that's called diffraction. Now, between refraction and diffraction, we are going to focus on diffraction. And that's going to be the next part of this online lecture module. Now, particles, they behave differently. So particles, if we throw a pebble in the water, we know that there's just a gradual change. It does not undergo refraction. And also, if we have a beam of particles and we aim it at a small hole, what's going to happen is that some will just go right directly through linearly. Okay, so we don't have a bending of light around the hole. So that's going to be the differences between how waves and particles react in those environments. So let's go ahead and, oh, before I forget, I just want to talk about a prism because we'll have an experimental setup with a prism. Now most of us know that when you have white light and you put it through a prism, we see a rainbow, right? So it's going to separate into its component colors. All right, so each wavelength is refracted at a slightly different angle, and that's called dispersion. That's called dispersion. All right, so let's focus on diffraction for the last part of this module. And this is important for us for this module and for a future chapter. Now here we have an experiment where we have two adjacent slits, and what happens is that our waves start to interact. Now when they interact, we say that waves are going to be in phase or out of phase. So this top box right here shows waves that are in phase. And what I want to point out that if they're in phase, you get a bright region. It looks white right here. So you get a bright region. Now, if the waves are out of phase, you get a dark region. Okay. So waves will actually interact. They will interfere with each other. Okay. So, and that creates what's called a diffraction pattern. So here again is the diffraction pattern. So I just want to show you with this one because I just like the way it's set up. So you have what's called destructive interference or constructive interference. So if the wave is out of phase, I like this one because it shows the little plus sign in the middle here. So you're going to add those two waves. And then notice that you just get a straight line right here. And that's why we will see a dark spot. Okay, so if we add those two waves together, you just get this straight line, you get a dark spot. But what happens if they're in phase? So notice this picture here. So if you have the wave here, add to this one, they're right on top of each other and the amplitude gets larger. And then that's why you will see your bright spot. And what I want the takeaway from for this module is to understand diffraction and what the dark spot means and what the bright spot means. Dark spot means they're out of phase. Bright spot means they're in phase. But what's important for a future chapter is that if waves are in phase, it's called constructive interference. So your amplitude just got a lot higher, and that's where you see your bright region. When waves are out of phase, you actually have a dark region. So it's kind of like they canceled each other out, and you got this straight line. So that's the takeaway I want from that portion of this module. Okay, I hope this is helpful, and on to the next video.